Okay, we're going to crack on. So, everyone that's joined, thank you so much. Myself and my colleague David Collins are going to be delivering a masterclass about decarbonization technologies, and how you can leverage them to their full potential. Obviously, there's a lot in that, so we're just going to show you a small kind of output around that, and hopefully it gives you a good feel of how CoolPlanet is tackling decarbonization technologies with our current client base. Um, so before we get into the implementation of decarbonization, energy efficiency technologies, we're going to begin with kind of the enabler or a core leveraging factor around enabling those technologies. And that's true data, gathering data, organizing it and leveraging it to its full potential. So this masterclass is one of many in a suite around decarbonization. If you've missed one or two along the way, the previous masterclass was around data, ingesting data, collecting data, and finding the right kind of data to leverage and analyze. So here at CoolPlanet, we lead with everything around data, from analysis to front-end engineering to detailed design to implementation. And a big change for us all, not just here in CoolPlanet, but for every industry, has been the inclusion or the kickoff of AI. It's really compounded the output, the efficiency of the output, and the quality of the output. And I'll be touching on that as we go through this particular masterclass. So the content that I'm going to show you is live. It's live data from client sites that we've had sign off to demonstrate today. I won't be naming those clients, but this is real data coming from real sites. So Dave is going to go into different technologies, one of which will be heat pumps. So I'm going to focus my kind of output today around analysis, leveraging the data before you implement a capital investment project like a heat pump to reduce your scope one and your gas consumption on your manufacturing sites. So to begin with, I'm going to look at a dashboard and analysis around a three boiler system. Each boiler is around 10-ton output. And we're just going to have a brief kind of overview of this system. As you can see, here's the split of the boiler share output on the system. So boiler two taking up most of the load, followed by boiler one and boiler three. Overall efficiencies were calculated. You can see them here, very low, not anywhere near industry standard, and well below average. So when it comes to data with CoolPlanet and CoolPlanet OS, we combine subject matter expertise with the data and with metadata like P&ID drawings, O&M manuals, control strategy documents, um, and also we've started to leverage AI within the platform. So the next step in this particular analysis was to analyze each boiler over an annual cycle um, to see their efficiencies, their firing rates, and to try and establish a more optimized sequencing control for this particular system. And the beautiful thing about using AI, they can do certain tasks very quickly, very efficiently, with high quality output. So what you can see on screen is looking at the AI, and our platform is looking at the raw data over an annual period, 1 minute granularity, and it's creating a lookup table of steam output versus efficiency for each of the boilers. And then it's coming up with a more optimized and increased optimization sequencing control output. And it's visualizing what kind of impact that control, change in control would have. So what you can see on screen here is actual gas consumption, actual steam load over a 12-month period, and then the modeled output if we slightly change the control sequence on these three boilers and the ultimate savings from doing that. So 6.92%, it's not a huge amount, but on a system this size, it's worth around $200,000 a year. So if you see this trend graph here, we're looking at total steam actual output. Then we're using the model. So the steam output is going to remain the same, but we're generating that steam through a different kind of control strategy. And then we're looking at the actual gas and the modeled gas from this kind of complex simulation or calculation from the AI. And again, the beautiful thing about utilizing AI with your data, it allows, common engineers to carry out simulations that in the past required, some very specialized software and maybe subject matter experts that have a huge amount of experience and training to analyze that data. That's the power of AI. Now, this is just a stopgap. Obviously, we can see these low efficiencies. So changing the sequencing, getting that 200K in savings, that's just the first step and it shouldn't be the last step. Ultimately, we should be analyzing each one of these boilers and increasing that boiler efficiency. So this next dashboard, this next feasibility slash analysis dashboard is drilling down into one of those three boilers. And this was carried out on all three. So we're generating outputs, calculations around boiler efficiency. We're comparing it to what the SCADA system is saying on this particular site. And this boiler controller would have been programmed by the suppliers of this particular boiler. We're not quite sure how they calculated the boiler efficiency. So it's always good to double check and validate that efficiency output that you're seeing on screen. As you can see here, this is quite low versus what's been displayed on the SCADA, even though the SCADA output is also quite low. And then we're drilling down into different KPIs that validate that efficiency output. So fuel to steam ratio, you can see it's well below industry target for this size of boiler and this type of boiler. We're looking at the economizer effectiveness. Again, it's way below target versus industry standard for this particular boiler. And what's also, very, very important is to understand where these virtual or soft sensors, these calculated data points come from. So we always display, the calculations, the equations behind each particular output. So you can see very low economizer effectiveness, very high O2 in the combustion cycle versus industry standard, way above where you'd expect. Then we're looking at things like the combustion efficiency of the burner and comparing that versus industry standard. And again, it's well below. So the next step here is to increase all of those KPIs, get this efficiency of all three boilers up to acceptable kind of outputs. So just to show you guys what our AI feature kind of looks like on the platform, these are graphs that were created from raw data points. And if we hit this AI button here, it brings up a kind of text output bar where we will have prompts, generated prompts, but like any kind of AI chatbot, the user can ask whatever it wants. But this particular one has, could the performance of this particular system be improved? Now, this is looking at the raw data itself. It's looking at the P&ID of the system, and it's also looking at the control strategy, the O&M manual. So bringing in all of that context, all of that metadata, and combining it with the raw data. And this is the kind of output that it will generate. So this is, it gives a high level summary of the data that it's looking at, and then areas of inefficiency. In this case, we're looking at a refrigeration system. And what the AI is telling us is the floating head pressure control opportunity is very evident here. It goes down through, the calculations, how it's summarized, this kind of output, and also next steps. So a really important output within CoolPlanet OS is we can now capture this opportunity within our opportunity register, which would have been covered on a previous module. So I really do suggest if you didn't join previous modules to get that kind of download, reach out to our team so you can view those previous master classes. So when we're looking at heat pumps, we've looked at the thermal side of a particular site, and installing a heat pump is going to impact that. Now we're going to look at the refrigeration side of a particular manufacturing site, analyze that kind of asset and optimize it as much as possible. So when we come to the installation of a heat pump or any kind of decarbonization technology, we're dealing with much reduced optimized loads. So this particular dashboard, again, I won't go into full detail around it, but it's looking at four chillers within a HVAC system. Very efficient, modern, relatively new installation, and it's analyzing the data. So a subject matter expert in tandem with our AI is generating this kind of output. So they're looking at nominal kind of analysis procedures like the evaporator delta T, generating some linear regression models using two variables, visualizing that model against actual, and looking at other KPIs to validate previous kind of analysis. So the COP of the system, the power consumption per ton of cooling, and the cooling capacity of in tons. And then the real kind of power output comes from the AI in combination with the SME. So in this case, it's looking at the pump feeding the evaporator and how it's being controlled. It's using things like the affinity laws, and it's applying the cube law relationship to model out if we increased or optimized the control on this particular pump, how that would affect the overall energy consumption. So in this model, it's theorizing that we can achieve savings of 62% on the pump itself, and expected savings or a knock-on effect of that on the chiller, savings of 25 to 35%, but it's very confident in achieving 16%. So next step here was to implement those control changes, send a control change document to the client, they would implement it, and then we would carry out a measurement and verification analysis as we would on every kind of solution. So in that theorized analysis, the pump savings was 62. We achieved 58. You can see the before and after here of the pump energy. And similarly with the chiller, the before and after, and we achieved 31% savings. So across all four chillers, this equated to 133,000 in financial savings. So huge impact on cost and energy and carbon around your scope two. So now, once that's done, now we get into, the analysis, the front-end engineering, and the detailed design of a technology, a decarbonization technology like heat pumps, and we implement it. We implement that solution, and we carry out a measurement and verification dashboard. This particular one is around the installation of a heat pump. We can see the operational hours, the thermal energy that the heat pump is providing, the carbon savings, the gas savings, and the energy savings, and the before and after. And then we're also looking at operational kind of data, day-to-day data for the utility and the maintenance team here. This particular solution didn't achieve the exact savings that were theorized. We were around 20 to 30% under expected savings. Even though it achieved some really good, healthy savings, we were still below the target savings. And that's why it's so important to take a holistic view and the impact of when you install new technology, new equipment like a heat pump, and how it affects other systems on the site. So once we didn't achieve those savings, we drilled down further into one particular boiler on that system. We had optimized it previously, so you can see efficiencies are up to 86. Fuel to steam ratio is exactly where you want it. A boiler economizer is exactly where you want it versus industry target or standards. But then when we start looking at the combustion efficiency and the O2 levels, we started to see cracks in the system. So this is the combustion efficiency, this blue trend. You can see a really evident step change around here, and then a further step change around here. And that correlates with O2 levels. So O2 increased at the same period and increased again in this second period. So what happened here was the boiler was down for maintenance and insurance checks, and the controls weren't the same controls weren't implemented as before that check took place. And then this drop in efficiency was when the heat pump was installed. So because the heat pump was taking up, 30 to 40% of the thermal load on site here, this boiler's burner needed to get recalibrated to deal with its new nominal load. And it was as simple as that. But unless we didn't have the data and really interrogated it, and because the savings were so healthy, this could have been something that we missed. So data, AI, huge core enabler for decarbonisation technology and is well worth the effort and the time to analyze your data and really leverage it to its full potential. Now I'm going to hand over to my colleague Dave that's going to go through some real life scenarios around decarbonisation solutions, implementations, and costs and effects and outputs. Dave, if you want to take over the sharing.
Yep, will do, Dara. Thank you, Dara. So good afternoon, good morning, everyone. Hopefully you can see that screen there. So as Dara said there, we lead with energy efficiency first. And what I'm going to talk about now for the next 10 minutes or so is just some of our own personal experiences in recent years of various decarbonisation tech with a particular focus around heat pumps and battery projects. So to Dara's point, very important, obviously, we implement energy efficiency first. Lots of companies have been doing that for years. And really then when you reduce down your demand from a thermal, cooling, electrical point of view, then you start looking at your technology. So when we talk about electrification of heat, we are looking at identifying step one, what are your primary energy needs? And really it's what temperature you need that heat at. And depending on that for your site, your applicable process, it will come back with a different type of technology. So it might be a low temperature industrial heat pump, electric boilers, obviously waste heat recovery is an option. But as you start to move up the temperature gradients, different type of technology will apply. You then need to look at, again, from an electrification point of view of heat is, well, can my site handle an increased electricity load? Obviously, the goal is for a lot of companies reduce down that scope one emissions on site by reducing obviously our fossil fuel consumption on site, but that will come with an offset around scope two and additional electricity being required, which again can be purchased under green PPAs or renewable certs, but you still need to cater for that additional electricity demand. So as part of that, you need to look at the capacity of your site, your maximum demand versus maximum import capacity, and talk to the local network to see, well, actually, if I'm going to be adding half a meg, 2 megawatts of power to my site, will that be catered for? What's the timeline on that? Another important part of the payback analysis is spark gap. So is it actually worth the while to make the transition from fossil fuel to electricity from a cost benefit point of view? Because if that spark gap doesn't match the criteria and some of the efficiencies that you're trying to achieve with your technology, then there won't be a return on that investment. So again, important criteria to assess. Benefits. So again, lots of support schemes here in Ireland, around Europe and elsewhere around what can contribute towards the cost benefit of your project. So carbon tax, credit rates under emission trading schemes, obviously reducing down scope one emissions will give you those credits back to put forward towards the business case. So working out, speaking to the experts to see what incentives are available in your jurisdiction for particular projects. So some of these are operational, some will be one-off. So again, grant support schemes for renewable heat, for energy efficiency. Most countries will have that, so it's important to do the homework on that. And for multinationals with multiple sites globally, you want to learn from particular case studies on your sites, but you don't want to get those stuck in a rut. So this term of pilot purgatory, where a very successful project is implemented on one site within a multinational organization, but doesn't find its way out to others, that can't be the case anymore. You want to get those case studies proven within your organization and get them replicated across multiple sites, so that you can build out your multinational, your corporate roadmap for sustainability. Talking a bit about heat pumps then, again, we talked a bit about the temperature. So this chart here is taken from the internet, but it looks at different industries from chemicals, food, to glass. And this is outlining the temperature requirements, how much of your process demand, for example, here in food, you can get away with 80-degree heat. So in food, for example, it could be between 50, 60%. The balance is at a higher temperature, which will generally be steam. Again, that's what you need to look at when you're doing out your heat mass balance for your site, because a heat pump, a certain type of heat pump, may only offset a certain amount of your fossil fuel demand. Similarly, again, and I'm going to go into more real life examples here in terms of the CAPEX. As you're starting out your feasibility studies, you need to be aware of what the capital implications will be. So again, I'll show you some examples of what we've seen in the past 2 or 3 years working with some of our clients. But knowing the temperature requirements, the scales, the grid connections, and getting that into an overall CAPEX figure is going to be a key part of the assessment criteria, and bringing in those incentives as well. So the following here, again, without naming any of our clients by name, but I'm just going to put those figures up. This is an example, are examples of 4 heat pump projects that we've implemented on our client sites over the past 2 to 3 years. All of them are low temperature heat pump projects. So you can see there that they're producing hot water at a temperature of between 65 to 85 degrees C. But actually, very importantly, they're using different sources of prime for the heat pump. So this first one here is ammonia gas. So this heat pump is interfacing directly with the discharge gas on a refrigeration system. It's in a brewery, and it's taking that gas and absorbing it into the heat pump to produce hot water. It's sending that hot water out to 2 heat sinks on the site. One is a process-related heat sink. Another is back for boiler house feed water preheating. And you can see there that the total cost of that project of approximately 1.6 million equated to do a CAPEX of about 1,300 euros per kilowatt installed. The second project here is, excuse me, again, it's utilizing cooling water, and it's for a space heating application. So this site was using steam to send around their site, and using steamed hot water heat exchangers to supply their LTHW heating coils and air handling units and to generate hot water. This project interfaced with the return lines on the LTHW, so created a new hot water network. So that's why the cost here would have been that bit more substantial. But you can see there for the scale of the unit installed, 1 megawatt, you're about 2,500 euros per kilowatt installed for that particular project. The next project here is 0.5 meg heat pump producing 85 C water. Again, the source of the prime was cooling water from the site. This was an edible oil site. The only heat sink here was just a single heat sink to preheat incoming air for part of their process. It's a dryer application in their process. Again, previously the site was using steam to provide that source of heating for the air heating, and now they're preheating that air with LTHW coming from the heat pump. Still quite a complex installation, and it averaged out about 3,500 euros per kilowatt installed. And then this other final unit here on the slide is again about 0.5 megawatt, producing at a lower temperature, but it's for a space heating application in a pharmaceutical site. It had 5 heat sinks associated with it. And I suppose the interesting one about this is it was recovering heat at a lower temperature, but it was actually recovering from waste effluent that was being discharged to drain or to a treatment system. So again, the heat that was being recovered from there was being boosted through a heat pump and sent around via a new LTHW hot water network around the site. And it averaged just under 1,900 euros per kilowatt installed. So it's kind of hard when you look at that slide to say it's a rule of thumb is very much it's going to be between 1,000 and up to 3,500 euros per kilowatt installed, but it very does much so depend on the application on site, how far you need to route LTHW hot water pipework, and how many heat sinks you're interfacing with as well. And in the case of this first project as well, the complexity of integrating directly with ammonia gas as well also has its challenges from a point of view of control and mechanical installation. Something else to look at there, and I alluded to this on the previous slide, is that higher grade of heat that's required on some sites. So we've done a couple of feasibility studies on petrochem sites, on edible oil sites as well, where sites are using high pressure steam up to 6 bar, between low pressure steam at 4 bar, up to 10 bar and 18 bar systems as well. And again, what you're looking for here is, well, if you can have have a source of prime on the site, such as large cooling network, cooling water towers for part of their process, can you intercept that heat, bring it through a low grade temperature heat pump system, but then boost it up using mechanical vapor recompression? So we've done a couple of these studies here. And again, you're getting into another level of CAPEX here. You can see the budget here was over 40 million for this project, but it is producing up to 19 tons of low pressure steam, 2 tons of high pressure steam at over 18 bar. But you can see there the CAPEX here is at another level compared to the previous projects, nearly 3 million per megawatt installed. But again, this is the direction that companies are having to look at now when it comes to looking at a strategy to decarbonize their sites, because you'll only get so far with low temperature heat pumps. You need to look at combining that with mechanical vapor recompression. Talk a little bit about batteries for the last couple of minutes. So why do we do batteries? Obviously, you would know yourselves, it's from a power quality point of view, taking out those transient voltage drops, managing your MIC as well. If you're restricted on your MIC, having a discharge there from a battery to help overcome those peaks helps as well. And then also energy arbitrage is important as well, so that you can charge the battery at night using cheaper daytime or cheaper rate electricity, discharge it during the day when rates are that bit higher or during peak periods. There's also operational benefits, particularly here in Ireland, where you can avail of grid services by having a battery on standby to discharge to the grid or take load off your own site. But again, from a point of view of CAPEX, just to give you a flavour of a couple of projects that we've done, both studies for on and are implementing. You can see there this is a 2.5 megawatt hour battery. The one here on the right is the 6.5 megawatt system. You can see there again, due to complexity of the site and the difference between existing or new infrastructure required from an electrical point of view, the CAPEX per kilowatt can be between 1,000 or 400 euros, depending on the site itself. So very quickly to finish up, just some of the pitfalls when we talk about heat pumps. Some of our own lessons learned. Oil cooling systems is very important because these are essentially refrigeration compressors. The oil systems in them need to be cooled. So making sure you have a unit spec that either has integrated oil cooling or you may need to bring a secondary source of cooling to the unit is important. Flow switches as well. So you might be putting heat metering, electricity metering outside of the package itself, but having the OEMs, so the particular heat pump provider, having that flow switch integrated back to the control panel is key. EX zoning as well within the container, between the control sections, the BMS sections of a heat pump panel, making sure that is designed and specified to the correct standards is key. There's a couple of things there that we found out post installation that have resulted in retrofit with the OEMs, but you need to make sure they're addressed going on. I've touched on the benefits of ammonia prime versus cooling water. If you can capture the prime directly from ammonia, it is probably that higher grade of heat, but it does have that complexities. You need to know what you're doing. Working with designers and contractors who have that experience of working on refrigerant pipework is key as well. And then having that automated bypass as well around the heat pump, because when your demand might dip, you want to recirculate that already preheated water back towards maybe a buffer vessel. There's no need to send it into a heat pump if the demand isn't there. So I won't go through the rest of them just in the interest of time, but that's just a flavor of some of the things that we've picked up on over the past couple of years working with OEMs and on some client sites. Just to do a bit of a wrap up in terms of the business case. So here again, a couple of things when we're working with our clients that making sure there's a clear business case, there is certainty on ROI. So working out that total cost of ownership, bringing in the non-financial benefits as well. So often these might be related to maintenance. So you might have additional maintenance on a heat pump, but that will take maintenance off other parts of the system. Bringing those together to make sure that the investment is justified. That's what our clients want to work on. I've already spoken about the incentives as well. So that might start around local incentives for directly to the contribution towards the heat pump, but then the knock-on effect of carbon credits, phasing the investments, and if third-party finance is required as well, bringing that all together in the funding model is key. Making sure you don't disrupt the site. We want to, and having that backup as well. So I mentioned before about a pharmaceutical site maybe having a steam tap water heating system. Often sites want to leave that redundancy there to have the steam systems remain in place so that in the event that a heat pump is down for maintenance, the steam systems can pick up the load or often do that final temperature trim as well while the heat pump is operational. And then the other one then is getting your own teams updated in terms of those new technologies, because again, bringing heat pumps onto the site in terms of maintenance. And again, this might even go for more traditional technologies around CHP, gas turbines, getting your teams upskilled in those types of technologies for future maintenance management is key as well. And again, there's lots of training and accreditation out there Dara alluded to already about AI tools as well that can help teams do that. So I think we'll wrap it up there. I've covered a lot of this about reliance on the OEMs. You'll see it there in the decks. But again, making sure OEMs are on the hook from a point of view of proven data, performance, reference case studies, signing them up to performance contracts with regards to availabilities and coefficients of performance that will be achieved. So there's lots that you can lean on in terms of your OEMs and your energy services providers to make sure that you're protected long term when bringing in these new decarbonisation technologies onto your site. So that kind of concludes. We are slightly over time, but we can take a couple of minutes there if there was any questions in the Q&A to start us off.
Yeah, some questions came through, Dave. I just looking at time, I answered the first two. Do you mind if we want to hit the third one? And I might revert back and read out my answers to the first two. So the third one was, we've already implemented some heat recovery and basic optimization. What's next? How do you find the next 10 to 20%?
Well, the low-hanging fruit, that's great to hear. That's been hit. So I suppose without obviously knowing the intricacies of your site, to Dara's point of, you have as much data available coming off your SCADA system into an energy monitoring system that you're doing that offline analysis on, because you might, as to Dara's point there, when he was looking at the boiler example, how it was marrying up with a heat pump, even if you brought in a heat pump to your site, there's still opportunities there to trim the boiler operation as well and to make sure it's working efficiently. But I suppose if you've pushed the boat out so far in terms of energy efficiency, that's when you start looking back into your generation. So yeah, that's what we'd be recommending there, and listen, we're happy to help around that.
Okay, great. We've been told to wrap it up. So thank you so much, everyone that's joined today. And if there's any follow-up questions, please reach out to CoolPlanet and we will get back to you as soon as possible. Thanks for your time today, everyone.
Thanks, everyone. Have a great day.